So, question 10 from exercise 2.2. Let's start with 10 part 1, the area of the shaded segment. This should be pretty standard by now because it's the same sort of process every single time when you're working out the area of a segment. So, the area of the segment is equal to the area of the sector subtract the area of the triangle. And the triangle, of course, is triangle OAB. And the sector is also called OAB, it's just that we're looking at the whole sector. So first of all, the area of the whole sector, so all of this shape here. So the sector area is equal to a half multiplied by r squared multiplied by the angle theta in radians, so 5 pi by 6. So this gives us a value of 20 pi by 3 centimetres squared. Now, the area of the triangle is going to equal a half AB sine C. Remember, where A and B are two side lengths and C is the angle in between them. So it's a half multiplied by 4, multiplied by 4, multiplied by sine 5 pi by 6, and this comes to a value of 4. So the area of the segment would equal 20 pi by 3 subtract 4 centimetres squared. And if you worked that out as a decimal value, which is perfectly feasible, we may have done that, 16.9439 ... So 16.9 centimetres squared to 3 SF. So now let's look at part 2 of this question. So we have two circles, each of radius 4 centimetres, with each one passing through the centre of the other. And we've got to calculate the shaded area. So there are a few different ways of thinking about this, but hopefully you can see that this really relates back to the previous question. Now, if I join up this point here with that point there, so let's call that point O, that black dotted line is 4 centimetres, and if I join up O to B as well, that black dotted line is also 4 centimetres. Now, from here to here is also 4 centimetres. And if we're going from one centre of the circle to the other centre of the circle, you can see that we're going from centre to circumference. Look at the blue circle, centre is O, the circumference, that's a point P on the circumference, so that's 4 centimetres. So that creates a triangle, which I'll call OAP, which is equilateral, 4, 4 and 4, which means that this angle here, which you can see there as well, angle AOP must be 60 degrees or pi by 3 radians. Now, that means that this angle, AOB, is double what we've just calculated, so is equal to 2 pi by 3 radians. Now, if I draw a blue line that joins A to B, hopefully you can see that this blue stripy region here is a similar sort of region to the one we calculated in part 1, and that makes up half of the shaded region that we are actually looking for. So I want you to focus on this purple outlined sector here. Goes from A to O, down to B, and then all the way along here, and then P is that point there. Now, what we're going to do is calculate the area of this blue sector here, remembering that this angle here is 2 pi by 3 radians. So the area of the blue segment, it's the segment that we're working out the area of, is equal to the area of the whole sector subtract the area of the triangle, which is this red outlined triangle over here. So it's a very similar calculation to part 1, except the angle is different. So the area of the sector is a half multiplied by 4 squared multiplied by theta, which is 2 pi by 3 in this part of the question. And then we're taking off the area of the triangle, which is a half multiplied by 4 multiplied by 4 multiplied by sine 2 pi by 3. And this gives me the area of the blue segment as 9.8269 ... as a decimal form. Now, look at the diagram again. Can you see that the shaded area, the sort of mustard coloured, gold coloured shaded area, is made up of 2 blue segments. So the overall shaded area is equal to 2 multiplied by this value 9.8269, and that comes to a value of 19.653 ... 19.7 centimetres squared to 3 SF.